Okay, so let's go ahead and let's go over chapter 6. And we'll continue on with discussing force and motion. Can everybody see the slides here?
Yeah.
Okay.
Yeah.
Good. Okay. All right. So we're going to go back and discuss a little bit regarding friction. Friction is basically it's a key ingredient on how you get from point A to point B. If you don't have it, then there are certain things that just aren't going to be possible. If you didn't have friction trying to drive up an incline to get to the top, it would be almost impossible. You might even see that writing with a pencil, obviously some of the lead from the pencil or the graphite is left behind. And that way you can make the mark and we can all read what you're writing. So it's necessary. It's something that we need in order to be able to do some things that we need to do. However, overcoming friction can have its problems. So one of those is efficiencies in engines. And this is a fact I wasn't aware of, that 20% of the gas that's used goes to counteract friction in the drivetrain. That's quite a bit. Roller skates and anything that you want to remain in motion, those are all friction that are forces that involve friction, and we have to be able to account for that to accomplish what we need. So we've got 3 experiments here. If we take a book and slide it across the counter, we know that the book is going to slow down and eventually stop. So there has to be an acceleration that's going to be parallel to the surface and opposite for the direction of motion. If we push a book at a constant speed across the counter, then there's got to be an equal and opposite force opposing you. Otherwise, the book would accelerate. So again, that force is parallel to the surface and opposite direction of motion. So if we take a crate or some other heavy object that doesn't move and we try to push on it, to keep that crate stationary, an equal and opposite force must oppose you. And if you push harder, the opposing force must also increase. And if you keep pushing, eventually the opposing force will reach a maximum, which will then allow your force up against the crate to cause it to accelerate. There are 2 types of friction. You've got a static frictional force, and this is the opposing force that prevents an object from moving. It can have a magnitude of nothing up to a certain maximum. And once that's reached, then the forces are no longer in equilibrium, and then the object starts to slide. Its velocity will start to change. You've also got the kinetic friction force. This is unlike the static that is present whenever the object has yet to move. For the kinetic frictional force, the opposing force that it's going to act on an object that is already in motion. It just has one value, it doesn't change. And generally, the kinetic friction force is going to be smaller than the static. So let's take a look at this. Here you've got no attempt at sliding for this particular object. It's just sitting there. So there's no frictional force. There's nothing there really in this direction that's causing it to move, and therefore there's no frictional force present. Let's say you start to apply a particular force in this direction. You're going to start pushing on it. You're going to have a frictional force that's applied this way to try to stop that. And if I can magnify this even more, that frictional force is the static frictional force. If you'll notice, from B to C here, these vectors start to become bigger, which means that more and more force is applied. As more and more force is applied, the static frictional force becomes stronger as well. Since this particular force ends up reaching a maximum at some point, we're going to be able to increase this force up to a particular point in which it is counterbalanced, but eventually the static frictional force will be overcome. And that's what's going on here. This force is overwhelming whatever that static frictional force happened to be, and now the object is moving, it's accelerating. Once it starts to accelerate, then this frictional force changes from static to kinetic. So if we're going to have this thing move at a constant speed to continue, then we're going to have to weaken this particular force such that it matches this. Again, even though those forces may be matched, that doesn't necessarily mean the object comes to a stop. It just means it's moving at a constant velocity. What this graph attempts to show is the magnitude of the frictional force. It has a component as time goes from 0 up to the time where it starts to move. The frictional force, the static frictional force, increases. Once the object starts moving, then the kinetic friction force takes over and then runs at approximately constant amount. So if you actually take a look with a microscope at a particular surface, I mean, from eye level, it looks relatively smooth. But if you actually get up and you start looking at these particular surfaces, what do you find out? Are they really that smooth? If you take a look at it, what you'll find out is they're actually fairly jagged at a microscopic level. And the friction starts to occur whenever the jagged edges start to come in contact with each other. So for instance, two specially prepared metal surfaces can cold weld and become impossible to slide because there's so much contact between the surfaces. That's kind of unusual. Greater force normal to the contact plane increases the friction because the surfaces are pressed together and they make more contact. Sliding that is jerky due to the ridges on the surface can produce a squeaking or a squealing sound. That's always pleasant. So here's an example of two surfaces running across each other. You can see the jagged edges there. This is what we're talking about. So, what are the properties of friction? If a body doesn't move, then the applied force and the frictional force balance along the direction parallel to the surface. They are equal in magnitude and opposite in direction. Now, how do we calculate these frictional forces? For the static frictional force, it's got a maximum, and that maximum value is going to be some coefficient or some number that's multiplied by the normal force. In other words, the force of the object as it's being pulled down on that particular surface by gravity. And that coefficient there is called mu sub s. I'm not sure how familiar you are with Greek letters, but that letter right there is the Greek letter mu, lowercase. So if it's that particular value is called the coefficient of static friction. If the applied force increases beyond that, then that's when you start to see the acceleration of the object. That's when its velocity starts to change. Once the sliding begins, then you're dealing with the coefficient of, or the kinetic friction. And the way that is determined is you've got a mu sub k, which is going to be the coefficient of kinetic friction. That is going to be multiplied by the normal force. This is one convenient way of modeling friction. There are other ways to do it, but generally this is the easiest way to approach it. The reason we choose the normal force is that it measures how strong the surfaces are being pushed together. And in order to be able to figure out what these coefficients are, you got to do it experimentally. Now, that's not necessarily something we're going to have to worry about. Generally, in most problems here, I believe that number is going to be given to you. We're going to assume that this doesn't depend on the velocity of the object, and these equations are not going to be vectors or vector equations. So let's take a look here at the first problem. We've got a block that lies on the floor. So what is the magnitude of the frictional force on it from the floor?
Zero, because it's not moving.
That's right, it's not moving. If a horizontal force of 5 newtons is now applied to the block, but the block does not move, what is the magnitude of the frictional force on it?
Wouldn't it be the same?
Yeah, it'd be the same. It's just pointing in the opposite direction. The net force here is 0 because the block isn't moving. It's just that those 5 newtons are pointing in the opposite direction. So let's take a look at part C. If the maximum value, the static frictional force, the maximum of the block is 10 newtons, will the block move if the magnitude of the horizontally applied force is 8 newtons?
No, because it's not enough to overcome it.
That's right. That static frictional force has a maximum of 10 newtons, which means it's going to apply that force as needed up to a value of 10 newtons. Beyond that, well, we'll find out here. What happens if that horizontal force goes from 8 newtons to 12 newtons? Will the block start to move?
It will now because it's enough to overcome the static friction.
That's absolutely right. So what is the magnitude of the frictional force in part C? And to give you a hint there, the horizontally applied force is 8 newtons. So what's the static frictional force magnitude?
Is it equal to it?
That's right, because the block is still not moving. So the answer there is going to be 8 newtons. Okay. So for a force applied at an angle, so let's say we've got a block here, somebody comes along and is pushing it, basically down into the floor. we're going to end up needing the components. We're going to have to take that force and decompose it into its X and Y components. We're going to balance the vertical components, the normal force, the gravitational force, and the force in the Y direction. And then we're going to balance the horizontal components, which is going to be friction as well as the force in the X direction. And then solve for the unknown, and knowing that there's a relationship between the normal force and the frictional force. That might come in handy later on. Okay. Has anybody here heard of a drag force before? Or just the simple term drag?
Yeah.
Okay. Before we start discussing that, we're going to discuss what a fluid is, and that's basically anything that can flow. It's a gas or a liquid. That could be air, it could be water, oil, what have you. So when there is a relative velocity between the fluid and an object, in other words, if one is moving at a certain speed relative to the other, you're going to have a drag force. The drag force is going to act like friction. It's going to resist the direction of movement. Let's see. Okay. Gives it. If you want to get real fancy with it, a drag force can have an equation something like this, where you've got, this is the relative velocity, you've got the air density represented here, you've got an experimentally determined drag coefficient, you've got the cross-sectional area of the body here, and why they didn't include the 1/2 here in with the experimentally determined drag coefficient, I'm not sure, but this is one representation of the drag force. Sometimes it's maybe just proportional to the velocity as opposed to the velocity squared. Drag force can be, it can have be presented in several different ways. It just kind of depends on what model actually fits the situation you're working with. So let's say you've got a cat, and as the cat is falling, as the cat's speed increases, the upward drag force increases until it balances the gravitational force. So in other words, as the cat is falling, the air is going to be pushing up against it, and it's going to increase in force until the acceleration becomes constant. So in other words, you've got the cat, let's say you're holding it there, you let it go, you can see that the drag on the cat is beginning to increase, and it will eventually increase such that it counterbalances the force of gravity. I'm not advocating dropping cats from high places to see this. I'm just saying if you were to take a stuffed cat and you were to drop it, then you could kind of see what's going on there. So the drag force from the air opposes a falling object. So in other words, if I take the drag force, which is pushing up, and I subtract the gravitational force, I should come up with mass times acceleration. That's the net force and Newton's second law. So once the drag force equals the gravitational force, the object falls at a constant terminal speed. And that speed is determined with this particular formula. So The terminal speed can be increased by reducing A. Does that make sense? Again, what we had been told back here was that A is the cross-sectional area of the body that's perpendicular to the relative velocity. So if I have a big, huge square that's falling towards the Earth, and I take that square and I reduce it, will the object start falling faster or slower?
If you reduce it, it'd fall faster, right?
That's right. If I take that same square and I continue to increase the area that's perpendicular to the direction of motion, is it going to fall faster or slower?
Slower if increased.
Yeah, the speed should decrease. And have either of you two been skydiving?
No.
Okay, I
Yeah,
haven't
not
either.
yet.
Oh, not yet. Okay, so there's still hope yet. One of the things that they do here to control their descent is to increase the amount of area that they have as they fall. So if you want to increase how quickly you're falling, you just point your head towards the Earth. If you want to slow down, you have your entire body falling perpendicular to the Earth. So let's take a look here. Speed of a raindrop. So a spherical drop feels gravitational force. If you want to express that in terms of the density of water, then you take the gravitational force, and that's equal to, oh, where did all of this come from? Well, the gravitational force is going to be mass times gravity, right? Well, there's gravity. So all of this velocity times rho here, must be the mass. This is going to be the volume density multiplied by the volume. That will give you the mass. And if it's a spherical raindrop, then this becomes this. So the force of gravity turns into a whole bunch of other terms. So you want to plug this into the terminal velocity equation. Boy, you got a lot of work ahead of you here. The force of gravity, we know that this is equal to that, so we put all of that mess in here. We know that the area is going to be pi r squared. That's the cross-sectional area of the raindrop. So we put all that information in here. Try to go through and simplify as much as we can. Like the pi's cancel, 2 of the radius cancel here, leaving just 1 up here, so on and so forth. We put all the information in here, and then we determine the terminal velocity of a spherical raindrop. That's kind of neat. Okay. Circular motion. We're going to recall this from last time. Circular motion requires a center seeking or a centripetal acceleration. That acceleration is going to be the same as the velocity squared divided by the radius. So let's say you're a passenger and you've got a car that's rounding a curve. The car accelerates towards the center of the curve due to the centripetal force provided by the inward friction on the tires. There's friction again. Your inertia makes you want to go straight ahead. In other words, you want to stay on the same path that you're on. So you may feel friction from your car seat and may be pushed against the side of the car. That's always an important point to lock the doors. These inward forces keep you in uniform circular motion in the car. So let's say here for a space shuttle, the shuttle is kept in orbit by the gravitational pull of the Earth, so it doesn't go floating off. That's acting as your centripetal force. This force also acts on every atom in your body and keeps you in orbit around the Earth. So you would float with no sensation of force, but it's always there. May not feel it, but it's there. And centripetal force is not really a new kind of force. It's just simply an application of the force in a circle. So force is equal to mass times acceleration, but we have discovered that centripetal acceleration is the same as the velocity squared divided by r. So a centripetal force accelerates the body by changing the direction of the body's velocity without changing its speed. In other words, that velocity is going to change as you're moving around in the circle, and this acceleration helps change that velocity. So let's say you decide to take a hockey puck and you tie it onto a string, and let's say you start moving it around in a circle. So the tension of the string is going to be pulling on that puck, and that's going to be supplying the centripetal force necessary for this velocity to continue to change its direction as you move around the circle. And the reason is because you've got this force that's pulling it in. So, as if you have either of you been to an amusement park?
Yes.
Okay. Have you chosen to ride a Ferris wheel?
Yeah.
Okay. So, you know what a Ferris wheel is. Basically, you've got seats mounted on a tall ring that rotates around a horizontal axis. So when you ride in that Ferris wheel at a constant speed, what are the directions of your acceleration and the normal force as you pass through the highest point, the lowest point, and how does the magnitude of the acceleration at the highest point compare to that at the lowest? Let's see if I can draw this. My tools here are kind of limited, so we've got our Ferris wheel here, and we've got our point, the highest point here. So that'll be our highest point. And the question's going to be, what are the directions of your acceleration and the normal force? When you're right here, which way are you accelerating? I'll give you a hint. Towards the center of the circle. What about the normal force? Is the normal force pointing the same way?
Wouldn't it be pointing upwards against gravity?
Generally the normal force, yeah. It's going to be pointing this direction since your acceleration is, well, let's see, let me make sure I'm reading this right. From the always upright seat as you pass through the highest point. Yes. What about at the lowest point of the ride? Draw that again. What about here? Which way is the acceleration?
Upwards.
Mm-hmm. And then which way is the normal force going to be?
Down.
Mm-hmm. So How does the magnitude of the acceleration at the highest point compare to that at the lowest point? If it's going to be uniform, then the magnitudes have to be equal. Oh, wait. The acceleration is upward. The normal force is upward. I'm sorry. I made a mistake on that. I think I told you that it was down. It's actually up. Let me draw that again. So both the acceleration as well as the normal force are going to be pointed this direction. So the acceleration is always going to be the same, but how do the magnitudes of the normal forces compare at those two particular points? I'll give you a hint. It's going to be greater here than it's going to be up there. And this is because it's because of the direction of the acceleration and the direction of gravity. All right, so here's another one. A bicycle is going around a vertical loop. So you've got Diavolo and the bicycle. Wish I had a better map than this. So the normal force is going to be from the overhead loop, and then the net force provides the towards the center acceleration, pointing downwards. At the top of the loop, you're going to have the normal force and the gravity pointing in the same direction. And since gravity is going to be negative here, that's going to end up being minus v squared over r. If you're going to solve for the velocity here, seems to me there's a little bit missing out of this particular description, like the problem itself. Let's go ahead and skip that for now. I mean, you can kind of see how the force is put together and where the velocity is, but it doesn't really tell you that it's trying to solve for the velocity until right here. I wish that had been written out a little bit better, but it wasn't. To solve for the velocity, what they've done is they've reordered this particular equation, substituted in the values that they knew, which again, they're not telling us here, and came up with the velocity. So we've got a car in a banked circular turn. We've got our radius. We've got the velocity of the car here. We've got tilted normal force supporting the car and provides the towards the center force we're seeing here. And so the gravitational force pulls the car down, and the acceleration is going to be inwards. If you go through and do some trigonometry here, you find out that f of n times sine of theta, which is going to be f n r. They don't really tell you that. So it should be this vector is going to be equal to the mass times the acceleration, which is minus v squared over r. They sum the components along the vertical direction. Eventually you can come through and you can determine what the angle is between the normal force and the vector, the normal vector in the y direction. I think they needed to explain these problems a little bit better than the way they left them here. Not real happy with that. So at the end here, you're seeing a summary of all of these particular concepts. I will have the lecture notes posted for you. Giselle, have you had a chance to go through and start working on any of the homework problems?
Yes. So.
Okay. Again, remember, I'm probably going to drop the lowest 3 homework grades. I mean, we've got 20 chapters that we have to cover according to the book and the description of this course in the course catalog. But I don't want anybody to feel like they're already getting behind. One other thing I would suggest is that if you have any issues with any specific problems that you can't figure out, put them in the muddiest point for each week. That way I can sit down and kind of go over it and kind of sketch out what a solution would be. You guys have any other questions at this point?
No.
Okay. How about the labs? Have you guys had a chance to look at those?
I haven't.
Okay. The first lab, let's see, I can't remember. I think the first lab is going to be due a week from tonight. So if you guys can sort of get together and compare results on that and write up a report, I'd like to see it a week from tonight. And this is on lab number 1, not lab number 2. Okay. Anything else?
No.
Nothing else for me.
Okay. All right. I'm going to be, I will be actually speaking with Tracy here at some point. So if you see her in class, whenever she can give me a call, then I'm trying to get her oriented as to where the homework is and where the other elements are in the course. If she happens to ask you guys, and I don't know that she will, you can also help kind of orient her as to where things are. But that's all I've got. So.
All right, yeah, that sounds fun.
All right. I will see you guys here next week, and please stay away from the COVID. It ain't good for nobody.
Yeah.
All right. I will talk to you guys later.
Okay.